Okay, fam. Hey, sorry we had to cancel class and go virtual today, but I think you can tell from how I sound that it was probably the best decision. So I'm going to try to whip through this lesson so that you're not spending too much time just staring at a screen because goodness knows that can get boring. I did have some really cool demos planned for lab, and we'll do those when you guys return to class because I do want you to see them. As far as your credit for this class, you will need to comment on the video in YouTube to tell me that you've watched it. And for lab, go to the assignment in Teacheries. There will be a video there for when we did the same lab from 4 years ago. Everyone needs to watch the video. And then it will be the assignment is set as a file download upload. So you'll need to get together with your team in your forum and discuss how you want to complete the lab. It will be one per team. The only person uploading should be the captain or whoever the captain designates. So in all, I should get 4 total uploads from the entire class. Then what I'll do is I will distribute those uploads amongst everybody else's gradebook accounts so that everybody shows that they've completed the assignment. So it's going to be one per team, but I only want that one upload. There's an answer sheet attached to the assignment, so complete that. And if you have any questions, let me know. Okay, let's roll. So today we're going to be talking about, solutions, concentration, and molarity. So solubility and a dissolving process. Let's start here. Solubility and polarity are related. Solubility, again, is the ability of a solid, liquid, or gaseous chemical substance referred to as the solute to dissolve in solvent, usually a liquid, and form a solution. They're not always a liquid. Remember, solute is what is dissolved, and a solvent is what does the dissolving. Solubility is also a measure of how much solute can be dissolved in a solvent. And solubility of a substance depends on the solvent used as well as temperature and pressure, and we're going to see why those things matter. If you look at our graphic here on the left, we have solution, and then we have a suspension. Remember, a suspension has particles that are sufficiently large enough to settle to the bottom of your container, um, and those particles are going to be, they cannot dissolve in the solution, which is why they're going to settle out. And then you know that if you have a chemical reaction in solution that produces a solid, we call that solid a precipitate, and we say that it crashes out of solution. But your new vocabulary word is the part that doesn't crash out, the part that remains in solution, and that is called the supernet. So why is it possible to overdose on vitamin A, but not vitamin C? So excess vitamin A collects in body fat because it is fat soluble. Excess vitamin C is eliminated in urine because it is water soluble. So this is important to understand. Here are some natural sources of both vitamin A and vitamin C. And you probably aren't going to OD by eating too much king mackerel, though I don't, what? Sorry. Too much of this king mackerel here or chicken liver. But people do take supplements, right? People take vitamin pills. You can take all the vitamin C you want. Now, if you take an awful lot, you're going to wish you didn't because you're going to pee a lot and then you're going to get diarrhea because your body's going to go too much water soluble, need to get rid of liquid, and that's not going to be a ton of fun. But some of these fat soluble molecules, you only have but so much fat in your body, and it can only dissolve but so much of the fat soluble vitamins. So yes, there are certain vitamins that you can overdose on.
Even
Oh,
though I'm
good
51, I don't
Lord.
feel
Of all the
51.
commercials
A
we
couple
get.
months ago, I discovered stribectin's facelift.
Yeah,
I've
facelift.
had this question a couple of times. Lindsay, could you please explain to us what it means when you refer to a fat-soluble vitamin versus a water-soluble vitamin? So I'm going to explain all of that and the significance of that in this video. We speak about nutrition and overall health, it's obvious that vitamins play pivotal roles, each having unique attributes that influence our health. These vital compounds segregate into two primary categories: fat-soluble and water-soluble vitamins. In this video, I'll clarify for you which vitamins are water-soluble and which are fat-soluble. I will also explain why it is important to make this distinction when it comes to supplementation. First, we'll look at water-soluble vitamins. Water-soluble vitamins are akin to fleeting heroes. They exhibit the propensity to dissolve readily in aqueous, otherwise known as water-based solutions, when they enter our bodies. We know that there are 9 water-soluble vitamins. The B vitamins, folate, thiamine, riboflavin, niacin, pantothenic acid, biotin, vitamin B6 and vitamin B12, and vitamin C. However, there exists a caveat. For the most part, these vitamins are not stored in the body. Our organism lacks the capacity to store water-soluble vitamins for extended durations. This necessitates recurrent replenishment through diet and sometimes through supplementation. Without the frequent ingestion and consequent absorption of these water-soluble vitamins in the intestines, deficiencies and ensuing health-related repercussions can occur. For example, a deficiency in thiamine or vitamin B1 can result in a condition known as beriberi. Your body needs thiamine to break down and digest the foods you eat, to keep your metabolism going, and to help your muscles and the nervous system to do their jobs effectively. A deficiency in this vitamin leading to beriberi can affect the cardiovascular system or central nervous system, and deficiency is most often associated with alcohol use disorder, secondary to malnutrition and poor absorption of vitamins in these individuals. Moreover, deficiency of any of these water-soluble vitamins can certainly lead to clinical syndromes with some severe health implications like the one we just discussed. Water-soluble vitamins are vital for our growth, our development, skin health, nerve function, heart health, and red blood cell formation. While the overall deficiency in North America is rare, as I mentioned, it can occur in conditions like alcohol use disorder, malabsorption syndromes where a person is not able to absorb the proper nutrition from their diet, strict veganism, or malnutrition. On the other side of the spectrum, we have fat-soluble vitamins. These include vitamins A, D, E, and K. These vitamins are stored in the body, which is very different from the aqueous vitamins that are not stored. It's important to note that having a fatty meal with a fat-soluble vitamin will help to increase its absorption. They are absorbed into the small intestine as part of newly formed micelles, which are lipid clusters containing hydrophobic groups or water-fearing groups internally and hydrophilic or water-loving groups externally. This process depends on the secretion of bile and pancreatic enzymes. After absorption through the cells in the intestinal wall, these cells are known as enterocytes. Fat-soluble vitamins are packaged into something called chylomicrons, or small fat droplets, and then they're secreted into the lymphatic system. Eventually, they do enter the bloodstream. Unique characteristic of fat-soluble vitamins lies in the fact that contrary to water-soluble vitamins, fat-soluble vitamins are stored in various tissues, allowing them to be retained by the body for a more extended period compared to water-soluble vitamins. This leads us to the question of the buildup of fat-soluble vitamins and potential for toxicity. While fat-soluble vitamins provide essential functions, you need to be cautious about overconsumption. Excessive intake of these vitamins can lead to toxicity, resulting in various health issues. For example, oversupplementation or overexposure of vitamin A can lead to hypervitaminosis A, causing a range of symptoms including headaches, papilledema, seizures, skin issues, and liver damage. Another example would be vitamin D. Although rare, hypervitaminosis D can occur with excessive intake of supplements and vitamin D fortified foods, which can cause gastrointestinal problems, hypercalcemia, which is too much calcium building up in the blood, and bone and joint pain. Moving on to vitamin E. Hypervitaminosis E is also rare, but it can result from oversupplementation, and this is especially contraindicated in patients on anticoagulants, otherwise known as blood thinners, due to its ability to thin the blood, thus preventing the blood from clotting normally. Finally, vitamin K toxicity is uncommon but can happen in certain situations and lead to hemolytic anemia, jaundice, and even liver damage. Understanding the difference between fat-soluble and water-soluble vitamins is crucial for maintaining optimal health and understanding the cautions that are warranted with any kind of supplementation. It's not just about getting enough vitamins, but also ensuring a balanced intake to avoid deficiencies as well as toxicities. So, next time you reach for that vitamin supplement, remember that just because it's a vitamin doesn't mean that it doesn't have potential side effects. As always, too much of a good thing is indeed too much. I hope this was helpful. Thank you so much for joining me. Take care and stay healthy. Bye-bye.
So why did I think she was Canadian? Did you see that up there? Well, she said North America, but if you were listening closely, you probably caught a couple of boots. My grandfather was from Nova Scotia, so I could say this, and I have lots of family in Canada. But the one that did it for me was process. That's a dead giveaway that you're Canadian. Process instead of process. So, yep. Excuse me. All right, moving on. Okay. So, like dissolves like. This is a big one. Commit this one to memory because this will come up again and again. Like dissolves like. So, what's this mean? Polar substances dissolve polar substances. So, polar molecules, ionic compounds will go together. Nonpolar substances dissolve nonpolar substances. So, you have nonpolar molecules and organic compounds. So, these things will go together. Like dissolves like. Polar dissolves polar. Nonpolar dissolves nonpolar. When a substance can dissolve in another substance, it's said to be soluble. When it cannot, it's said to be insoluble. But we have two specific words that we use when we're referring to liquids, and that is miscible, liquids that are soluble in each other, and immiscible, liquids that are insoluble in each other. So, water and oil in this case, over here with your immiscible, that shows that they are insoluble in each other. So why is ethanol, which is an alcohol, miscible in water? Ethanol, like water, is polar, and molecules can also form hydrogen bonds. And over on the left, you can see this would be an ethanol molecule and water, and you can see where they can bond. Solubilities of solid compounds. Greater surface area speeds up the dissolving process. So solubility of both ionic and molecular substances generally increases with increased surface area and increased temperature. So you have a direct proportionality between temperature and solubility and surface area and solubility when it comes to solid substances. So if you have a candy cane versus the same mass of sucrose in granulated form, and you put them both into a glass of water, obviously your granulated sugar is going to dissolve more quickly than your solid massive candy cane. And that has to do with surface area. More sucrose is exposed to water in granulated form than it is when you're dealing with a solid mass of sucrose, like as in a candy cane. So when you dissolve ionic compounds, they are going to disassociate, which means they separate from their lattice into their individual dissolved ions, which we understand. If you put sodium chloride into water, you get sodium and chloride ions. And we call that process hydration. It's the surrounding of those dissociated ions by the water molecules. And you don't have to memorize a lot of these solubility statistics because it's already been done for you. The work's been done. You can find out that fluoride is soluble in ammonium, but it's only slightly soluble in lithium, and it's insoluble in magnesium. Like, it's all been done. So we have great solubility rule charts that you can use. And they even group them by, alkaline metals and transition metals and whatever. So this sort of resource is very, very handy. Saves you a lot of experimental effort that you don't need to put forth because here it is. So let's talk about saturation for a bit. So the best way to talk about saturation is to discuss degree of saturation. So an unsaturated solution contains less than the maximum amount of solute that is capable of being dissolved. So this could be dilute, but it doesn't have to be dilute. It can be, getting close to saturated, but still unsaturated because you can still add more solute. When you get saturated solution, that means you have reached the maximum amount of solvent that has been dissolved. Um, and any more solute added will sit as crystals at the bottom of a container. And then supersaturated is when it contains more than the maximum amount of solute that is capable of being dissolved at a given temperature. Well, how can you have more than a maximum? Well, basically, what you have to do is change something about your situation. And typically, what we change is temperature. If you can try this at home, but you can get like a measuring cup of water and add some sugar to it, and you will have an unsaturated solution. Keep adding sugar to it until no more dissolves, and you'll have a saturated solution. Pop it in the microwave for a few minutes and heat it up. You'll be able to add even more sugar to it. Even though you had reached a point where you couldn't add more at room temp, now you're going to be able to add more because we've increased the temperature. When it cools back down to room temperature, it is super saturated. And if you leave it long enough, it may start to form some crystals. That's how we make rock candy. So, solubility equilibrium. All right, this is a type of dynamic equilibrium that exists when a chemical compound in the solid state is in chemical equilibrium with a solution of that compound. So I'll give you a minute to look at this graphic here, but it says salt is initially put into water and begins dissolving. Salt continues to dissolve, however, salt ions will also precipitate. Because the salt dissolves faster than the ions precipitate, the net movement is towards dissolution. Eventually, the rate of dissolution will equal the rate of precipitation, and the solution will be in equilibrium, but the ions will continue to dissolve and precipitate. An equilibrium can exist between a partially soluble substance and its solution. So let's talk about that for a minute with our good friend here, good friend Professor Dave.
Why wait? Start your MD this May at Ross Med and begin hands-on experience within weeks, not months.
Professor Dave here. Let's talk solubility.
He knows a lot about the science stuff. Professor Dave
Everybody
explained.
gets sad when we see short-haired Professor Dave.
When we first discussed solubility, we learned that some ionic compounds are water soluble and will completely disperse in solution due to the ion-dipole interactions they will make with water molecules. We also learned that other ionic compounds are water insoluble and will not dissolve at all, remaining completely in the solid phase. Beyond this, if the components of such a compound find each other in solution, they will precipitate and leave solution completely to form a solid. This is actually a slight oversimplification that served its purpose at the moment, but now it's time to get a more sophisticated and quantitative understanding of solubility. So let's get a closer look. It's true that many ionic compounds are completely soluble, but the reality is that even the ones that we call insoluble will dissolve to a minuscule degree. Whatever the degree to which dissolution occurs for a particular substance, we can communicate this using the solubility product, abbreviated as KSP. Let's look at a substance like silver chloride, which we label as water insoluble. As we said, if there is an excess of it in water, it will dissolve to a tiny extent and cause a dynamic equilibrium. Some ions dissolve as other ions rejoin the lattice. Just as with any other type of equilibrium, there must be an equilibrium constant to describe it, and that's the solubility product. As we might guess, this will simply be equal to the product of the two ion concentrations in solution, each raised to the power of their stoichiometric coefficients, which in this case is simply 1 and 1. Notice that we do not include the solid itself in this expression, as we do not include solids in equilibrium expressions. The smaller the constant, the fewer the ions that will be present in solution, and therefore the less soluble the substance must be. And compounds that are extremely water insoluble will have KSP values on the order of 10 to the negative 30, negative 50, or even smaller. Let's make sure we can write these solubility products for various equilibria. Take something like calcium carbonate. First, we must write out the complete equilibrium. Upon dissociating, this will form a calcium ion and a carbonate ion. Therefore, the solubility product will be equal to the product of these two ion concentrations. If we have something like magnesium hydroxide, it's the same thing, except that dissociation produces one magnesium ion and two hydroxide ions, which means that hydroxide ion concentration will be squared in the solubility product expression. We can even do this for something more complicated, like apatite, which is a mineral. This will dissociate into 5 calcium ions, 3 phosphate ions, and a hydroxide ion. So the solubility product expression will look like this. In this way, a number of ionic compounds that we previously deemed insoluble should actually be categorized as slightly soluble. If we have a way of measuring ion concentrations in solution, we can calculate the KSP value for a given substance. Let's say we have a saturated solution of milk of magnesia, which is magnesium hydroxide. This is slightly soluble and dissolves according to the following equilibrium. Say we measure the resulting magnesium ion concentration as being 3.7 times 10 to the negative 5 molar. What will be the solubility product for magnesium hydroxide? First, let's write the KSP expression for this substance, which we derived earlier. Notice that hydroxide concentration is squared due to the coefficient in the equilibrium. Now, if this is the concentration of the magnesium ion, then the hydroxide ion concentration must be precisely double, since there are 2 hydroxide ions for every magnesium ion in this substance. So all we need to do is plug these 2 concentrations into the expression, evaluate, and we will get 2.0 times 10 to the negative 13 for KSP, which will be a unitless constant, just like other equilibrium constants. We can also go the other way around and predict the concentrations of ions that will result in solution when dissolving a substance with a given KSP.
I think that Ross did an amazing job. I am prepared to go and start my residency.
Let's say we place copper 1 bromide, which has a KSP of 6.3 times 10 to the negative 9, in aqueous solution, which will then generate copper ions and bromide ions to some extent. What will be the molar solubility of this substance, meaning how many moles per liter of the formula unit will dissolve? To find this, we can write the solubility product expression and use this to construct a simple ice chart. In this, we will not list any values for copper bromide, as this is a solid. The ions themselves will start at 0. The change will be x because of the 1 to 1 to 1 ratio, and this means that the equilibrium concentrations of the ions will also be equal to x. Therefore, the KSP will be equal to x squared, and x will be 7.9 times 10 to the negative 5 moles per liter. This is the molar solubility of copper 1 bromide, which in this case is simply the concentration of copper ions and bromide ions in solution at equilibrium. This can be a little trickier if the KSP equation involves exponents, but the process is essentially the same. Let's look at calcium hydroxide, which has a KSP of 8.0 times 10 to the negative 6. Say we place this in aqueous solution, which will produce some calcium ions and hydroxide ions. Again, let's write the KSP expression, noticing that the hydroxide concentration must be squared, as there will be 2 hydroxide ions for every formula unit of calcium hydroxide that dissolves. Then, when we make the ice chart, we will notice that again the initial concentration of each ion will be 0, but the change will be x and 2x respectively due to the stoichiometry of the equation, and the equilibrium concentrations will also be x and 2x. Putting these into the KSP expression, we get that the KSP will be equal to 4x cubed. Now solving for x, we divide by 4 and then take the cube root, leaving us with 1.3 times 10 to the negative 2 for x, which will therefore be the molar solubility, which we can interpret as the solubility of the solid expressed in moles per liter, or the moles of the solid that will dissolve per liter of water. So now that we've learned a bit about the solubility product, it's time to learn a few applications of this concept. But first, let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, Professor Dave Explain.
So don't get too hung up on that, but I want you to understand it as a basic concept. Okay? All right, so now let's talk about gases dissolving in liquids. So we have another gas law, guys. This one is Henry's law, which says that at a constant temperature, the amount of a given gas that dissolves in a given type and volume of liquid is directly proportional to the partial pressure of that gas in equilibrium with that liquid. So say we have a commercial fizz saver pump, and it pumps helium under pressure into a soda bottle to keep gas from escaping. Will this keep the CO2 in the soda bottle? So your answer for this is no, because Henry's law states that the partial pressure of the same gas in a solution. I'm sorry, let me read that again. Henry's law states that it is the partial pressure of the same gas in a solution, which keeps the gas in solution. Increased pressure of helium will have no effect on the solubility of CO2. But if we look back here at where it says at a constant temperature, the amount of a given gas that dissolves in a given type and volume of liquid is directly proportional to the partial pressure of that gas. Keep in mind that whole bit about, you open your soda bottle and it makes that sh sound. That's because you've reduced the pressure in that container. And you've got carbon dioxide escaping, and that's because the pressure of the carbon dioxide outside the bottle is less than the pressure of the carbon dioxide inside the bottle. It's specifically the carbon dioxide that matters. So let's talk about temperature and gas. So gases dissolve in liquids better when it is at a lower temperature. There's an inverse relationship between the temperature of a liquid and how much gas that dissolves in it. The warmer it is, the less gas you can dissolve. The colder it is, the more gas you can dissolve. So let's just say that global temperatures rise. And this could be due to anything, changes in solar radiation, position of the Earth relative to the sun. This could cause ocean temperatures to rise. So what would you expect to see with regard to atmospheric CO2? Well, you would expect to see more of it, because if the oceans are warmer, they can hold less dissolved CO2. And this is one reason that it can be difficult to pinpoint the exact impacts of man-made emissions on climate change, because when levels of CO2 increase, is it because the temperature of Earth and its seawater has increased? Or did Earth's temperature increase because the levels of atmospheric CO2 increased? So this comes up when we do Earth science. And it's an interesting concept. But if for some reason our Earth warms due to factors like, increased solar radiation, for example, then you're going to get warmer oceans and you're going to get less CO2 dissolution, which will produce more carbon dioxide in the atmosphere because less is dissolved in the oceans. And then you have a warmer global temperature. but also a warmer global temperature could be produced by excess CO2 in the atmosphere because CO2 in the atmosphere can cause the Earth to become warmer. So it gets to be sort of a chicken or egg situation. Um, so keep that in mind because that will come up again. If you haven't already done Earth science with me, it will come up when we do Earth science. All right, so physical properties of solutions. So electrical conductivity in solutions. So conductivity is the measure of the ease at which an electric charge or heat can pass through a material. An electrolyte is a compound which produces ions when dissolved in solution, such as water. And a non-electrolyte is a compound which does not produce ions when dissolved in a solution, such as water. Oops, sorry. So in this case, you've got three examples. If you have ethanol, which is an alcohol, you're not going to see any conductivity because there are no dissolved ions, um, which is going to make it more difficult for electricity to pass through that particular solution. But if you have potassium chloride, it's going to be highly conductive. And if you have acetic acid, which is vinegar, it's going to have low conductivity, but there are some free ions, so you will get some conduction. Now, you may have heard of electrolytes being in your Gatorade or your Powerade, and why is that important? Well, your nervous system and your musculoskeletal system, the way they interact is entirely based on electrolytes. It's all about electrical conductivity and electrical signals. So you do need that those electrolytes in your body in order for you to function. So your homework's going to be on this topic, and we'll come back to that. Well, let's talk for a minute about hydronium ions. Why is this such a thing that acid, remember I just showed you acetic acid is a little bit conductive? Okay, well, we're getting here. So hydronium ion can be formed when an acid is present in water or simply in pure water. And its chemical formula is H3O plus, and it can also be formed by the combination of an H plus ion and an H2O molecule. So H plus ions are present in acids, right? So when that comes in contact with water, you get H3O plus, which makes perfect sense. So it says if an acid is present in water, you can get hydronium ions. That's because you have both components there. In water, it has to do with some of the water dissociating, and then you get an H plus ion that will come in contact with the water molecule. So hydronium ion is has trigonal pyramidal geometry and is composed of 3 hydrogen ions and 1 oxygen ion. Because hydronium and hydroxide ions, remember hydroxide is OH negative, can move without actually moving, meaning that they sort of form and they kind of go back and forth, like you can see in this picture, between forming and then swapping back into a water molecule. They don't have to plow their way through a solution by shoving aside water molecules as other ions do. Um, Solutions which are acidic or alkaline have extraordinarily high electrical conductivities, and this is why. It's almost as if the charge kind of hops from place to place because these ions will form and then switch back, which will cause make a path for electrical conductivity. Yeah. Anyway.
Water is usually thought of as a non-conductor. However, very sensitive devices can detect some conductivity in water, no matter how pure it is. Even very pure distilled water contains some ions. Why is this so? In any sample of pure water, almost all of the water molecules remain as neutral water molecules and don't react chemically with each other. However, about 2 out of every 556 million water molecules will react chemically with each other. We'll show 2 of them here with their bonding and non-bonding electrons. The purple one will act as an acid, and the blue one will act as a base. A hydrogen atom breaks away from the water on the left and leaves its shared electron behind. Because it has lost an electron, it acquires a positive charge, becoming an H plus ion or a proton. Because the OH has gained an electron, it acquires a negative charge, and it's called a hydroxide ion, with the formula OH-. The proton moves to a non-bonding electron pair on the other water molecule. We'll change its color to blue. The positive charge is now distributed over the whole ion instead of just being on the H that it came with. This is now a hydronium ion, with the formula H3O+. The process can be summarized by an equation. When a proton is transferred from one water molecule to another, the water on the left gains a proton to become a hydronium ion, and the water on the right loses a proton to become a hydroxide ion. However, when a hydronium ion in water encounters a hydroxide ion, a reverse reaction can also occur, where a proton is transferred from the hydronium ion to the hydroxide ion, forming two molecules of water. Because both the forward and reverse reactions continuously occur, this is an equilibrium, so we use a double arrow here. Instead of writing these as two separate water molecules, we can combine them to show them simply as two water molecules. We'll move this arrow over a bit. This equation is a very important equation to know. It's called the ionization of water equation. Sometimes it's called the self-ionization of water, because water acts as both the acid and the base. In Chemistry 12, we refer to it simply as the ionization of water. At a normal room temperature of 25 degrees, the reactant liquid water is highly favored. To illustrate this, we show there's more reactant than products. The relative sizes of the letters here are very qualitative and nowhere near to scale. The concentrations of hydronium and hydroxide ions are only about 2/billionths that of water. The KQ expression for this reaction is equal to the concentration of hydronium times the concentration of hydroxide. Because the water is a liquid, it is not included in the KQ expression. Because this equilibrium constant is specifically concerned with water, we change the symbol from KQ to KW. KW is called the ionization constant of water. The value for KW is temperature dependent. At 25 degrees, the value is 1 times 10 to the negative 14th. It is very important to remember that the value of KW is 1 times 10 to the negative 14th only at 25 degrees Celsius and at no other temperature. But KW is always equal to the concentration of hydronium times the concentration of hydroxide at any temperature for which water is in the liquid state. Because all aqueous solutions contain water, and all water ionizes to form some hydronium, some hydroxide ions, we know that all aqueous solutions contain some hydronium and some hydroxide ions. By definition, for any aqueous solution, if the concentration of hydronium is equal to the concentration of hydroxide, the solution is said to be neutral. And if the concentration of hydronium is greater than the concentration of hydroxide, the solution is said to be acidic. And if the concentration of hydronium is less than the concentration of hydroxide, the solution is said to be basic. These are the definitions we'll use for neutral, acidic, and basic solutions. You must make sure that you know these.
So that's how you get hydronium from water. And we're going to watch one more Professor Dave here talking about electrolytes.
Turn buys into flies
Yeah, get your credit
with the
card.
Southwest Rapid Rewards Plus card.
Okay.
Ooh, grilled cheese. Steak sliced in flour
Always.
dust. Nature's own perfectly crafted bread. You're fancy now.
Hey, it's Professor Dave. Let's talk about electrolytes.
He knows a lot about the science stuff. Professor Dave explains.
Anyone who is a fan of sports beverages has heard of the word electrolyte before. But what does this word really mean? This term refers to a substance that, when dissolved in water, will dissociate into positively charged and negatively charged ions, which have the ability to conduct electricity in solution. A substance that will not dissociate into ions when dissolved in water will not be able to conduct electricity and is therefore called a non-electrolyte. The greater the extent to which a substance dissociates, the stronger an electrolyte it is. So as we look at different types of electrolytes, we will be focusing on the efficiency of the dissociation. If a substance completely dissociates in solution, it is a strong electrolyte and will conduct electricity very well. If a substance only partially ionizes in solution, meaning some particles dissociate and some do not, this will be called a weak electrolyte, which will still conduct electricity, but not as well as a strong electrolyte. And as we said, a substance that does not dissociate at all will be a non-electrolyte. We can categorize substances as being one of these three things by measuring the electrical conductance of their corresponding aqueous solutions. In order to conduct electricity, a substance must contain freely mobile charged species, such as the case with metallic wires, which allow for the free movement of electrons. In a solution, these freely mobile charged species are the ions that result when a substance dissociates. The more ions there are in solution, the greater the conductivity and the stronger the electrolyte. And we can measure the current flow or simply observe the brightness of a light bulb included in the circuit to gather this kind of data. Let's categorize electrolytes a bit further. Something like potassium chloride will dissociate entirely, so it is a strong electrolyte. It is also an example of an ionic electrolyte. These are ionic compounds that will dissociate in aqueous solution to give individual cations and anions. The dissolution occurs because the cations and anions will be able to make ion-dipole interactions with the water molecules that comprise the solvent. And this energy storage, combined with the greater disorder of the solution over a crystallized ionic solid, is what results in spontaneous dissociation. The ions will therefore be dispersed throughout the solution in order to maximize solvation. That is, to maximize the ion-dipole interactions that are occurring by allowing for as many water molecules to interact with each individual ion as possible. This will be the case with most ionic solids, which is why ionic solids, whether comprised of monoatomic ions or polyatomic ions, tend to be strong electrolytes. Acetic acid, being a weak acid, will only partially dissociate, so it is a weak electrolyte. This is also an example of a covalent electrolyte because the molecule contains strictly covalent bonds, and unlike ionic solids that allow their interionic attractions to dissipate in favor of solvation, these covalent species undergo an actual chemical reaction with the solvent molecules in solution to form charged products. These will typically be strong acids and bases that either donate a proton to a water molecule or remove a proton from a water molecule. For example, hydrogen chloride is a covalent compound. There are no formally charged particles in this substance, only neutral atoms. But when dissolved in water, it will become hydrochloric acid, which is a strong acid, and will completely transfer all of its protons to water molecules, resulting in a certain amount of hydronium ions and chloride ions. This means there will be enough ions in solution for it to be considered a strong electrolyte, so it will conduct electricity. Of course, the identity of the solvent plays a big part in this, as in order for hydrochloric acid to donate a proton, something must accept that proton. So, if hydrochloric acid were to be placed in an aprotic solvent like ether or hexanes, this would not result in an electrolytic solution, as these solvents can't accept any protons the way a water molecule can. But for aqueous solutions, let's keep in mind that strong acids and bases will be strong electrolytes because they ionize completely in solution, whereas weak acids and bases, like acetic acid, will only partially ionize and will therefore be weak electrolytes, as they will generate relatively small concentrations of ions in solution. Lastly, something like ethanol won't dissociate almost at all, so it won't generate any current, making it a non-electrolyte. That's because it doesn't have appreciable acidity or basicity, so the reactions it will make with water molecules in solution will be negligible. The same can be said for sugar and many other covalent compounds, or water-insoluble ionic compounds. We want to make sure we can identify substances as being strong electrolytes, weak electrolytes, or non-electrolytes. So let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials.
Yes, we love you, Professor Dave. Okay, so why does tap water conduct electricity, but distilled water, not so much? It's typically because you have dissolved ions in your tap water. A lot of the time that's fluoride, chlorine, stuff like that. All right, let's talk about colligative properties. Okay, colligative properties describe the physical effect of a solute on a solvent. Colligative properties are those that depend upon the concentration of the solute molecules or ions, but not upon the identity of the solute. Colligative properties include vapor pressure, lowering, boiling point elevation, freezing point depression, and osmotic pressure. So, examples of the four colligative properties. Elevation of boiling point. So this would explain how you can cook spaghetti faster in salt water. Okay, when people put salt in their water to cook their spaghetti pasta, they're often doing it just to season the water so that it gives a little more flavor to the spaghetti. Now, when it says faster, it's going to take a little longer to reach that boiling point because you have raised it. So it's going to be above 100 degrees Celsius. So it's going to take longer to heat. So what is meant by faster is that once it's boiling at a hotter temperature than it would be had you not added the salt. So therefore, the cooking process will go faster. Depression of a freezing point. So this is why we put salt on the roads and the sidewalks to keep ice from forming, because instead of freezing at 0 degrees Celsius, it's now going to freeze a little lower than that. Lowering of vapor pressure. This is why you put antifreeze in your radiator to keep your car from overheating. And osmotic pressure. This explains why your little brother killed the family fish when he placed it in tap water or pure water while cleaning the tank. Pure water if you've got a saltwater fish, tap water or salt water or anything else if you've got a freshwater fish. Why does spreading salt on an icy sidewalk cause ice to melt? Again, because it lowers the vapor pressure and the freezing point of the ice, causing it to melt at a lower temperature. So it can be below freezing outside, and you can keep the ice from forming on your sidewalks and your roads. So let's talk about surfactants. We did briefly discuss them last week. Now we're going to talk a little more about them. So a surfactant is a substance which tends to reduce the surface tension of a liquid in which it is dissolved, concentrated at the interface of the two phases. Detergent is a type of surfactant or a mixture of surfactants with cleansing properties. The way they work, again, you have a surfactant, which has a hydrophilic or water-loving head and a hydrophobic or water-hating or water-avoiding tail. And then when you get this surfactant stabilized oil droplet, remember this is called a micelle. We've talked about this before. This is why you can use like micellar water to take off your makeup and clean your skin or whatever. Soaps are a cleansing and emulsifying agent made usually by action of alkali on fat or fatty acids and consisting essentially of sodium or potassium salts of such acids. And an emulsion is a fine dispersion of minute droplets of one liquid in another in which it is not soluble or miscible. This is like mayonnaise is a great example. Mayonnaise has some vinegar in it and some other things that contain water, but then it also has oil in it. So you have water essentially, and then oil, which don't mix with each other. But if you make mayonnaise, like I have a mayonnaise recipe from my great aunt, and you have to like whip it forever because what you're doing is dispersing those minute droplets of the oil within that of the water, and that produces the mayonnaise. If you heat mayonnaise up or put it under certain conditions, you can watch it separate, which is really gross, by the way. All right, so we talked about surfactants and babies and their lungs. So here's how that works.
Some premature babies spend weeks or months in a neonatal intensive care unit, often due to their lungs not being fully developed. At Valley Presbyterian Hospital, we spoke to Dr. Nushin Zaman, who discusses the pulmonary challenges that these babies face.
We can actually have babies that are where moms have been pregnant for only 6 months. So that's considered about 24 weeks of gestation. Now, these babies, as you can imagine, have pretty underdeveloped lungs. And that's definitely part of the problem. The other part of the problem is the lungs actually make a thing called surfactant. And this surfactant helps coat the lungs and reduces the surface tension so you can blow it up. If you can imagine blowing up a balloon, initially when you blow it up, it's very difficult. It's the same thing for babies. When they open up their lungs, it can be very difficult. And if they don't have enough surfactant, this babies develop what's called respiratory distress syndrome.
There have been major improvements in neonatology to help these newborns.
Babies used to have almost 100% mortality rate back in the 1960s, 1970s, if they had severe respiratory distress syndrome. But there was actually an amazing invention that was created back in the late 1980s and was approved by FDA in the early 1990s, where they invented surfactant that we could actually give to the babies. So now we can actually intubate the baby and give the surfactant straight into the lungs. And this has improved their outcomes significantly. Babies that didn't used to survive before can actually survive and do very well.
Medications given to the mothers-to-be also resulted in better outcomes.
It's been shown if the moms, when they're pregnant prior to delivery, if they actually get the steroid shot, usually betamethasone or dexamethasone, it helps stimulate the baby to make some of the surfactant on their own. So a lot of those babies, if the moms have had the shots before they're born, those babies tend to do better as well.
Dr. Zaman tells us about the specialized treatments for other serious respiratory problems these babies may have.
Babies have meconium, which is stool. Okay, and it's thick and gooey and goopy, and that's usually the first stool that babies have. The problem is sometimes when babies are term or they're being born a little bit later, they start stooling inside into the amniotic fluid. But if they're born and they actually inhale some of this amniotic fluid, they can actually become very sick. Some of the babies develop a thing called persistent pulmonary hypertension. And what that is, the blood that goes from the heart to the lungs to get oxygen, those blood vessels end up becoming constricted. And not enough blood goes to the lungs to get oxygen to go to the rest of the body. And there's definitely interventions that we can improve this. And one of those things is called nitric oxide that actually helps dilate the vessel so more of the blood can go to the lungs, get oxygen, and go to the body. Now, some of these babies, they do become sick enough where they actually have to be placed on cardiopulmonary bypass, and it's called extracorporeal membrane oxygenator or ECMO. These we only have in tertiary centers. But up until that, we can actually manage a lot of these babies who can become pretty sick.
So I don't want to like traumatize anybody, but if you want to watch how they give surfactant to babies, there are videos of it, plenty of them online. You can look it up yourself, but they will intubate the baby, which means they do have to use one of those they call it a tongue blade, kind of holds your tongue out of the way, and then they stick the little tube down into the lungs, right? But when they went to go to give surfactant to the babies, they will actually stick a tube down into the lungs and inject the surfactant directly into their lungs, like it's like a oily liquid, and they will squirt it right directly into the lungs. All right, so moving on. A water softener removes calcium and magnesium ions from water. Why does a softening agent improve the cleaning ability of soap? The ions removed from the water would have formed insoluble compounds with the soap. This is how you get soap scum. Yuck, right? No fun. So your homework is going to be the following. Sports drinks such as Gatorade or Powerade are marketed to athletes to replenish electrolytes lost by the body during exercise. Research why the human body needs electrolytes, what types of electrolytes are used by the human body, which of these electrolytes are lost in the greatest amount through exercise, what types of electrolytes are in these drinks, and whether or not these drinks can be beneficial or necessary for athletes to remain healthy. Write a short paragraph to share what you've learned, and you will add that into your teacher ease. All right, so gang, thank you so much, and I will see you next week.